Okay, so this is my attempt number 2. Right, what we should be seeing is we're on the magnetism and electromagnetism topic. I'll cut this out for you and put it into a checklist, and we're getting towards the end where we're talking about transformers, step up and step down transformers, and next lesson to finish we'll look at the formulas and some exercises that we can do with the formulas. But then what we've done is all the stuff about motors, and we'll have done transformers, national grid, transmission of electricity and everything. So let's get rid of that, we don't want that. You guys should have in your Google Classroom here the classwork task for today: magnetism, electromagnetism, motors, generators, national grid. Remember, if you've got any questions and stuff, it's always the best idea to ask the question here in the task. Yeah, put your comment on the task itself, and then everybody else gets to see the answer as well, and it saves a bit of time me answering individually every single person. And believe me, everybody has got questions. It's perfectly normal, so don't feel embarrassed. And if I answer you, then I'll probably also answer the question that somebody else is thinking about as well. So what we're going to do is first motors, generators, and fill in the Google Doc, and then we're also going to do transformers and national grid and fill in the Google Doc that goes with that. So this is a Google Doc, so I'm going to have this open as we go through the PowerPoint to fill in, and we're going to start off with motors and generators there. Now, one of the problems is some people don't have PowerPoint. This is why I'm doing it in the video, so you can see all the animations. So first we're going to look at the link between movement, magnetism and electric current. And in the photo you've got lots of different apparatus and stuff. For example, there's a guy cleaning a window with a magnet or something, a floating toilet seat. Oh my god, that would be quite useful for some of you. Magnets to hold somebody against a wall and switch on and off. Okay, but what I want you to think about is what is the link between movement, magnetism and electric current. And if you note in your Google Doc what you think the link is, and also I want you to think about what the name of the famous scientist is that studied this, and what famous rule he came up with using one of his hands. So carry on. Okay, how do the magnetic field and the current affect a wire? What would happen when the current flows through a wire that's held perpendicular at right angles to the magnetic field? What happened? It moved up. Okay, except the guy that is holding it is cheating a bit there. So again, you've got in your Google Doc place to answer that. Okay, so carry on. Direction of the force on the wire can be reversed in different ways. You can reverse the current and the wire will go down. You can reverse the magnetic field and the wire will go down. From the first example, if we reverse the current, it went down, and then we reverse the magnetic field, it will go up. So note this down in your Google Doc. Direction of the force is relative, or is linked to the direction of the magnetic field and the direction of the current. And if you've stopped the video and you've written this thing down in your Google Doc, then you should have written down it's Fleming who described this with his left hand rule. Thumb motion, or thumb is the thrust. First finger the magnetic field, second finger current, and it's important that your fingers are all at right angles. So how can the size of the force be increased? Got three factors. One is increasing the current, more cells, more current, more force. How can the size of the force be increased? Increase the strength of the magnet, use a bigger magnet. How can size of force be increased? We increase the length of the wire that's inside the field by, for example, using a coil of wire. We can increase the force. How do magnetic field and current affect on a coil of wire? So when a single wire in the magnetic field moves in the magnetic field, the current runs through it. What happens to a coil of wire? So the current here is going that way, this direction, or that way. Draw on this. If it lets me. Lets me draw down there, but it won't let me draw there. So on this side, current's going that way. On this side, the current's going that way. And if you use your left hand rule, because the magnetic field is going that way, so field first finger, here the current is going that way, so the force would be down. Using left hand rule, first finger's going that way, it's going that way, so my thumb's going up. So on that side of the coil, it's going up. Let's turn it on. Okay, and we see the arrows there. Now we'll see the forces, and it will turn like that. But it's not a very good motor if it just does that. So how do we keep it rotating? And how do we stop these wires from getting tangled up? That'll be the next one. What we can do here is we can add what are called brush contacts and a commutator, so that the current is always going up that way on that side, and the current's always going down that way on that side. And having a circle here or a commutator means that that can turn and brush against these contacts, and the current is passed. And once it gets halfway through its turn, the current changes direction. We'll see that in a minute, I'm sure. So let's go back to so can you do the true or false exercise in your thing? Got 3 factors of force and stuff. Do the true and false here, and then find out the answers. I don't know, stick a few in there, and then we'll solve it. Pretend that I can't remember. What do I do with my pointer now? Switch the pen off. Okay. Turn that on. Next. Okay, there we go, sorry. So we've done that. And then have a look around your house and put in your Google Doc how many items you can find that contain an electric motor. So you need to pause the video and do that. Here I was talking about the commutator or the brush contacts. So the electric motor uses the effect that we've seen before. Switch it on. Switch it on. So as the coil turns, here we've got the forces. But what's about to happen here is, once we've got to this point, contacts aren't touching, but the coil has been moving, so it's got a bit of momentum that's turning it. So it will carry on turning a little bit more, and now when it touches, the current from here is going through this side of the loop, and the force is down, and coming back through this side, and the force is up. So the current is always travelling up that side, down that side, because of these brush contacts and this split ring, which is called a commutator. Okay, so sometimes it's better to see this in 2 dimensions. Okay, so there's a magnetic field, There's a current. Switch current on and off. See what way it's going through the wire, and you see it changes direction in the coil. Forces turn on and off, or if I want to slow it down a bit, see better. See it happening more slowly. Get rid of the magnetic field, and get rid of the forces, and you see the current, because of the commutator, changes direction. Okay, it's a lot better if you can do this yourselves in PowerPoint. So would the same strength motor be used in both these, electric drill or a little fan? Can you note that down in your Google Doc? If we go back in Google Doc, we should be down here. And now we're going to go into induction and generators. Ooh. So, what happens if instead of having a current moving through a wire that's in a magnetic field, how about we move the wire in the magnetic field and we get a current? So if you've got two of these things, we've got movement, field and current. If you've got two of them, it's going to produce the third. So if I've got current moving through a wire, I get a magnetic field. Remember, that's a right hand rule. If I've got a wire moving through a field, I get current, and if I have a current moving through a wire that's in a field, I get movement. So I think we've got a bit note down. Okay, the answers here in your Google Doc. So when the current flows through a wire in a magnetic field, the force is created, it moves a wire. The opposite is also possible. If a wire is moved in a field, current can produce. The real physics term is, to be sexy, electromagnetic induction. Induction also occurs if the magnet is moved in a coil of wire. But then again, what's happening is the field of the magnet is moving and the coil is stationary, which is the same thing as the wire moving and the field being stationary. Okay. What's important is, like with the left hand, to have your fingers perpendicular. All of these have to be perpendicular. If any of these are parallel to each other, nothing happens. So, if we move the magnet inside the coil, what happens? The current is induced in the coil. Put it back out. Current is induced in the coil. If you notice, opposite direction. Positive as it went in, negative as it came out. So, magnetic moving inside the coil will produce current. Direction depends on the direction of the movement of the current. When the magnet is still, there's no current. And you can do that until you put it in, pull it out, put it in, pull it out, and now I've got bored. So generator is a device that converts mechanical energy into electrical energy. It's opposite of an electric motor. In power station, this is what we use in generators to make electricity on a large scale. Mechanical energy produced by the turbine turning, and power by steam in coal, oil, gas and nuclear power stations, or wind in wind turbines. Remember the topic on energy. In hydroelectric power stations, it can be water that turns the turbine. So, alternating current generator, what we do is we avoid having the split ring that we had with the motor, and in this one we have just two coils, two circles, cylinders that turn attached to each side of the coil that's in the field. These are what we call brushers, because these contacts that go to the electric circuit, they stay still and the ring turns, but they do touch, so they brush against the ring. and the coil turning is producing a current, and that current is alternating backwards and forwards, backwards and forwards. So here we can look at the graph of the current, and it's alternating current, like from when we saw the electricity topic. DC electricity would be continuously the current flowing in the same direction, so it would only be a straight line on one part of the graph. Let's get rid of the current from the diagram, get rid of the forces. The forces are coming from the turbine turning the coil. So that's the current that's produced, and the current changes direction as the coil turns. Forces from the turbine is turning it always the same direction, and the field is always the same direction, but the current we get is alternating current. Current changes direction. How can we change the size of the current? We can increase the speed, increase the strength of the field, increase the number of turns on the coil, or we can increase the area of the coil that's in the magnetic field. Now, these kind of things, what we want to do is note down in your Google Docs for me. The power station generator electromagnet is often used because this gives a stronger magnetic field than just a permanent magnet. And these beasts are what we have in the power station. They generate 20,000 volts alternating current. What we've got here is this will be the turbine and this will be the generator. And you can see an axle joining the two there. So, can we note this down? Okay. Rotate the coils slower, rotate the coils faster, use smaller coils, use larger coils, use fewer coils, use a stronger magnet, use a weaker magnet, use more coils. You guys note them down, pause the video, and then we'll check. I've got it completely wrong, but anyway, did it on purpose. So these increase the current, these decrease the current. So pause the video to note these things down. Now, I'd like you to do true and false. You can do this as well in your Google Doc there. So, true and false answers. I'm not going to solve this, okay? I'll let you do it and I'll mark it for you. Those of you that can use a PowerPoint and do it, then do it first, write your answers down and then solve, please. Test yourself. So it's the best way to learn. And then summary, okay, we've got some key words. We've got a bit of a game here, unscrambling words, okay. So there's the first one. I won't tell you what the answers are. Second one, pause the video. Third one, pause the video. Fifth one, pause the video. Sixth one, pause the video. Seventh one, pause the video. Eighth one, pause the video. And I won't show you the answers. Note it down in your Google Doc. See how many you get right in the quiz. In which direction will the wire move in this circuit? If you look at it here. So pause and write it down in your Google Docs if you're doing this on the video. Which of these will not increase the size of the force acting on a current carrying wire in the magnetic field? Pause it, write it down in your Google Doc. Which part of the motor is this? Here. That bit there. What is the role of a split ring commutating electric motor? Pause the video, write down your answer. Which of these will not increase the speed and strength of rotation of electric motor? Pause the video, write down your answer. Which of these will result in electromagnetic induction? Pause the video. Which of these statements is true? Pause the video. Which part of the generator is this? Right there. What is the role of a slip ring in an electric generator? Which of these will not increase the size of an induced current in a generator? So, write down your answers in your Google Doc for me and send them in. What I'm thinking is probably we could actually do these questions, this quiz, using a Google form. But I'm learning how to do this as well, so bear with me. And that's the end of that one. So